Hello and welcome to everyone, and thanks to everyone for joining us. My name is Glenn White. I'm also joined by Tim Milo, our SIMULIA application specialist, who's going to be driving the majority of today's presentation. And today we want to take you through some of the capabilities and tools available as part of the SIMULIA Abaqus analysis suite, which is really our next level solution for analysis. And today's session is serving double duty for us a little bit here this time around. You may be aware every Wednesday we present two webinars. We call them Wednesday webinar. We present one at 10 a.m. Pacific time. That is a demonstration of a particular product area or something of interest, show you what it does. 11 o'clock we present a product education session, really tips and tricks around some area of SolidWorks. We are also running a series this month we call May Simulation Month here at Hawkridge Systems. We're running a series of webinars where we're exploring how our customers use analysis tools. So today's session on SIMULIA Abaqus fits into both categories. So, just to talk about what we're talking about in Simulation Month, you'll see a lot of reports out there about companies' usage of analysis tools. We've got one on our website right now from Aberdeen Research company. It's called The Value of Virtual Simulation versus Traditional Methods. And they go out and they poll 5,000 people in industry, ask questions about how they're using analysis and come up with these numbers, these improvements of what best-in-class companies do. And when I read these things, I always ask myself the question, who are these companies? And, are they like the companies that I deal with every day, or are we talking to the Boeing and Airbus of the world? So we thought it'd be interesting to gather some information directly from our customers during this webinar series, and then share it back with you so that you can see that, hey, small companies in aerospace, just like me, if that's the case, are doing these things for analysis and kind of give you a sense of where you sit in the analysis spectrum. Okay. And so what I'm going to do to kick that process off is to ask you a couple of pieces of demographic information. Just 3 quick questions here that I'm going to launch some polls. And I really appreciate your feedback. All right, so the first question is, how many employees? How big is your company? Are we talking less than 30, 31 to 100, 101, 500, or 500 plus? Again, I'm just trying to get a general sense. And I'll share the information as it comes in. Looks like 30%, 60% of the people in this session are 100 employees plus, which is interesting. Okay, let's go ahead and close that down. Well, let's find out, what general industry do you consider yourself? Now, unfortunately, GoToWebinar limits me to 5 choices, so you may not be a perfect fit, but pick the closest that you can approximate. Okay. Some interesting results so far. A third of the people about a third of the people are identifying under energy, about a third under high tech, and a third under automotive and transportation, which is very interesting. Okay, so thanks for that information. And next up, last question for this little block is, how long, do you use SolidWorks, first of all, and how long have you been using SolidWorks? Just trying to get a sense of, how long 3D CAD has been in use in your company, or for you personally. All right, so we've got a good 40% of people, 5 years plus, another 30% or so, 2 to 5 years, and the rest split. Okay, great. So we'll stop at 2 other points, and we'll ask some of these questions. But so that's kind of the And we'll be sharing the summary of that information with no details, just the percentages, essentially. We'll be sharing that with you at the end of our series, at the end of May. Okay. But the star of the show today is a tool that is called Abaqus, right? Developed by the SIMULIA brand at Dassault Systems, so it's somewhat connected with SolidWorks, which is also a brand of Dassault Systems, but it offers advanced analysis capability. It's really a next-level analysis tool that complements and extends the functionality that we at Hawkridge talk about a lot that is available in SolidWorks Simulation Standard, Professional, Premium. And Abaqus is geared towards realistic simulation, about trying to approximate the real-life behavior of a scenario as closely as possible. Okay, so we're going to we use techniques like, really strong contact algorithms to do complex contact problems, highly nonlinear problems, look at fluid structure interaction, look at damage, look at composites, huge range of stuff that we can engage here to meet that goal of realistic simulation. And so how we consider this is when we talk about analysis a lot, we show slides like this. We talk about, the starting off with analysis with basic linear static stress analysis, moving up into considerations of, basic vibration and some thermal effects. And then when we get into SolidWorks, we assess some nonlinear and dynamic behavior. Abaqus is the next step that would sit up from there, using tools and techniques that just don't exist in the SolidWorks realm to do that realistic simulation. All right, as Tim's going to show you, still maintain an associative interface with SolidWorks. There's an incredible range of stuff we can do in that tool. Probably the most powerful FEA tool available on the market today, especially in nonlinear and contact behavior. And we can still maintain that sort of ease of use. So we've got very powerful solvers. Abaqus is associated with SolidWorks, but it doesn't live inside the SolidWorks window. You almost don't have the overhead of a CAD tool when you're doing that analysis, which can be both a benefit and sometimes a disadvantage. But it's got an incredible user community, right? All the way from academic use to industry use across thousands upon thousands of companies. And really flexible pricing and packaging that can make it, affordable or useful for companies of all sizes. Okay, so just some of the key capabilities. If you're watching a couple animations there, one of those animations is a crack propagation study, right, looking at a crack through a vessel. One at the top there combines deformable actions with rigid body motion of a crash test dummy in a highly nonlinear event, right, very rapid, sharp event. But we've got really rich material and mesh choices available to us. We can look at highly nonlinear, highly dynamic events like crushing, like crash, and we have damage capabilities, so we can look at how parts will actually fail under loading. And if you get into the composite realm, it's pretty some really complex and unique damage assessments for composites as well. And so Tim's going to take you through kind of the model prep and result interpretation stuff that we have available. And so at this point, I'm going to introduce Tim Milo, who's our SIMULIA application specialist. And we're going to work through 3 examples, show 3 really diverse examples. 2 of them are scenarios that we've worked with our customers on. The other one's a neat little application to show you how it works. So, Tim, why don't I hand you the presenter role here, and you can take it away.
All right. Thank you for the introduction, Glenn. As Glenn said, I'm Tim Milo. I'm the SIMULIA Applications Specialist here with Hawk. And I'm going to take you through a few analyses, starting with a dynamic analysis of a golf ball impact, which is the video you see on the left. I'm going to introduce the associative interface and go through some of the meshing approaches, setting up general contact, and assemblies in Abaqus CAE. So I'll start out with this assembly in SolidWorks. We have a fairly detailed model of a golf club and a ball. And what I'm going to do is come over to Abaqus, and I'm going to bring that assembly in. Here we just basically make sure that we've activated the SolidWorks associative connection, which we have done. And at that point, in SolidWorks, under Tools, Abaqus, Export, we'll go ahead and run that export. So you can see here now we have the assembly placed in Abaqus as it was set up in SolidWorks. So once we have an assembly, we can come down into the properties and start to look at the setup for the individual properties of the model. So here I've defined 3 properties to define the ball, and basically a steel material property for the head and shaft. The ball properties was able to find in some literature surveys of what people have done to try to analyze golf club impact. For the steel, it's a pretty typical steel in terms of a Young's modulus definition. If we want to go further down the tree, we can define plasticity, and with that we could either just define a perfectly plastic with a given yield stress, and we can go a step further and use stress strain data from tensile testing. For the purpose of this analysis, just wanted to look at a linear elastic model for the club. The core materials are kind of interesting. They're also elastic, but one thing you'll notice is rather than 30 million Young's modulus, we're on the order of 4,000 at the core, which is pretty soft, and the skin is more on the order of 35,000. We have some options for material damping and other things, and one of the analysis I did went ahead and defined a material damping, basically gave a beta damping term to damp out some of the high frequency response, if you're familiar with Rayleigh damping, and that's something I'll get into later. So once we've defined some material properties, and I've got some mesh models, I'm just going to copy one of these models so we can go through some of the property definitions and meshing steps that you can take. So we define a section for the shell, and in this case I gave it a 0.0125 thickness for the handle. And then we also assign the material property to the solid regions, which we're going to mesh in solid elements. Here in the meshing interface, it's pretty simple to set a general element seed size. So we can change that size and go ahead and remesh it. One of the things that you'll often find is you may want to check that your analysis is kind of independent of mesh size. Another thing that we can do, I'm going to go ahead and go back to the SolidWorks model, come into just the model of the club, and let's say we want to shorten that club. Right now it's 38 inches, we'll call it 34. And we'll send that back over to Abaqus. Alright, so now you can see that the shaft isn't meshed anymore, but basically we have our seeds that we've already defined are still persisting, and we can just basically remesh the part as such. So another option that we have in Abaqus CAE is the way to handle the shaft. There's 2 options. Basically, we can use either an inner-outer surface to define traditional shell elements through this volume, or we can use what are called continuum shells, which are a solid that you can define as one element through thickness. So it's a nice blend of the efficiency of a shell element, but the modeling simplicity of staying in solids. So this is the continuum shell model, which I'll zoom in here on the top so you can see that we do have just a single element through thickness. And if we look at the standard shell model, you can see it's the more traditional shell, where if we turn on the shell thickness, we can display that thickness, but it's essentially a 2D element. So once we've defined some element types, the next step is to define the type of analysis. And so I'll come into the step manager, and it's as simple as create, and we're going to create a linear perturbation frequency step. In the frequency area, we can define how many frequencies we want to look at. We're interested predominantly in the first bending mode, so I said we'll look at 2 frequencies. Once you've defined your steps, I'll come down to load and apply a boundary condition. You'll be able to see here that I essentially created a fixture at the top where the grip would be in the translation directions. So here we have a fully defined analysis. So at that point, we create a job, which I've got a few jobs that I've already run down here. So we'll go ahead and come in and look at the results for the traditional shell first. So here you can see the sort of, as you might expect, a first bending mode. It's on the order of 4 Hertz, which very closely matches one of the studies that I came across. So without too much time and setup, we can fairly closely approximate behaviors that were both tested and modeled and published. So that's a nice thing about literature search. Just basically look for golf club, abacus, and come across some pretty powerful work that people have done and shared. So now I want to take a look at the continuum model and see how that matches up. We might have noticed the frequency of the first analysis was 4.05 Hertz. And if we look at the frequency in this continuum analysis, it's 4 Hertz. It looks a little bit different. So here we can come into our scaling. And if we turn that scaling to 1, we get more of the shape that we might expect. So you have pretty easy control of the scaling, and you can turn off feature edges to give some flexibility for the types of plots that you'll make. So next, I'm going to take a look at that assembly that we brought in the standard copy. So since we created a copy of our original assembly, the steps persisted, and we can just basically create a run from that. We'll call it frequency short since it's the shortened club. And these modal analyses will run relatively quickly. It's somewhere on the order of 30 seconds. So we'll kick that off and let that run here for a bit. I'll start to introduce the this is the full assembly of the ball and the club, and what I did is I added sort of a rigid link from the end of the club up to a fictitious pivot point, which might represent the shoulder. I took that as 28 inches, and so once we've defined this whole assembly and a pivot point, I just come into boundary conditions, and this model is actually pretty simple in that the only boundary condition is that it pivots about that pivot I defined, and I created an initial condition where the whole assembly is rotating at 28 radians per second, which is a pretty healthy club speed from what I can find. That's right at 100 miles an hour. So we just define a pivot point and initial condition, and then we're basically set up for the impact analysis. The one other step that we take is to define a general contact. So the way that's done is in this interaction manager, just create general contact, and this is an explicit dynamics analysis. So in that we say we want to look at the contact of everything in the model. We assign it an interaction property, and in that interaction property we can look at things like tangential and normal behavior. In this case, I just said give it a friction coefficient of 0.8, hoping we might observe some spin. It looks like the short analysis is done, so we'll take a look at how that looks compared to the longer clubs. So you noticed that the first two had a frequency of 4.05 hertz. So we find shortening the club might increase the frequency up to 4.6 hertz. Just sort of a quick and easy way to check what a design change might do in terms of a frequency response. So now I'm going to go into the meshing of this ball. So you can see that the ball that I mentioned uses 3 different materials. You can see the outer skin here, and what I'm going to do is take away a couple of the 8 sections that I divided the 3 layers of the ball into and show you what the material distribution looks like. So one of the reasons that I sectioned this ball off is so that we could sweep hexagonal elements throughout the core. It gives us some nice control to have a uniform element size and no real small or pointed elements. That became sort of important because the elements where I used material damping was in the core. As I understand, they're a viscous element, and that kind of plays pretty predominantly into the ringing modes you get as you go through the impact. So now I'm going to show you the results of the original analysis that I ran of this Gulf strike. So we'll load up this result set, and first we'll play an animation of the whole system so you can get a sense that that club is spinning about the point that's the pivot point up above. We can turn on the viewpoint if we want to actually see that, and we're going to go ahead and zoom in to get a closer picture of what that ball does. One of the nice things in this visualization is it's pretty easy to come in and set different colors based on how what sort of graphical representation you want. If you're just plotting displaced shapes, and we can turn off those element edges. And here we have the animation, the impact. You'll notice that the shock wave sort of travels through the ball a few times. So this is an analysis done with no material damping applied. One of the trade-offs of material damping is that it takes significantly longer to run an analysis. So one of the things I did here was to run this analysis for a shorter time with material damping. And so maybe this one will run somewhere on the order of 10 hours. But you get some nice payoffs for that, which is when we animate this shock wave, which travels back and forth once, and basically that ringing is almost died off by the end of that shock wave. So there are a few other aspects of this analysis that we can come in and look at. I defined some nodes where we want to look at the history of different variables. So we can see that the ball slightly higher on the club, and then the end of the higher velocity is further out on the club. So at a quick glance, you can see that the ball is probably averaging about 2,700 feet, and the club end comes in, or just above the head is coming in at somewhere around 1,600 feet per second. If we want to see how adding damping affects that, it's pretty striking. So you can see that really damped out some of that ring, the sharp ringing that you got in the interior of the ball. and it also lowered the exit velocity a bit. So you have a ratio of somewhere near 1.4 of an average ball speed versus the club speed. And for a fairly simplified swing, what I could find, just doing a quick internet search, is people look for a 1.5 off the club, so we know we're in the right ballpark. All right, so now that I stepped you through some of the steps of bringing in and doing a golf club impact analysis, I'm going to turn the page and go to some of the basics of pipeline model that these use pipe-soil interaction elements. So you can see at the top of the screen, we have some elements representing a pipeline, which are in green, and then the pipe-soil interaction elements above them. And what these are is a way to apply far-field displacements along a pipe. You take the displacement between the pipe and the ground, and we can define material models that give you a force for a given displacement per length of pipe. So these models can resolve the ground properties, as well as that you can measure them, in that we can have a three-dimensional spring properties at every element along, a fairly complicated pipe and soil system, so that the resolution of this is really going to be as good as your measurements. So I'll take a quick, I'll show one of these types of pipeline models. So here, if we take a side view, we can zoom in and see that we have a sort of a step change along the fault line at the surface. And if we go ahead and turn up the beam profiles, and I'm going to exaggerate that by a factor of 4, we can see that along with figuring out the displacements along the length of the pipe, we can get at the stresses, and we can pick nodal forces at any given place if we have more detailed submodels for junctions and other things. So now I'm going to go ahead and change gears a little bit and go through an air spring suspension that we've simulated for automotive applications. This model is based around a cord reinforced air spring. Inside the air spring, we have an ideal gas law pressure cavity. This simulation I did in 3 steps, where there's an initial pressurization step with some extension allowed of the suspension. Once it's pressurized and the gas is basically sealed at a given volume and pressure, we'll drive that to settled and then drive it through a bump. We have an animation of that system with a lower control arm and the air spring constrained at the top just being driven through a bump. You can see in the graph on the right that through that you can track the reaction forces and sort of back out the spring rate behavior, including some of the dynamics of the suspension components. I'm going to zoom in on that a little bit and take a more in-depth look at an air spring model for a rolling lobe air spring. So this air spring is similar to the other, is built with reinforcements. So we used a Mooney-Rivlin hyperelastic shell model for the rubber material, and there was Kevlar reinforcements throughout the shell. We can vary the Kevlar orientation and sort of look at the effect of that on the output. So I'm going to switch over to the air spring model. I'll start with the assembly just to show the sort of full view of the system. We can take a cut so we can see the internal components. And we'll go ahead and color these by part. So we have our reinforced air spring. We have a foam or elastomeric type bump stop, and then we have the steel base. Or in this case, it's modeled as rigid since it's relatively rigid compared to the other components. Taking a look closer at the air spring, so I've defined material models for a bumper, which in this case we used a hyperfoam, and I found material properties for a very similar bump stop in the Abaqus help. So if you just come into the help and look for a hyperfoam, there are benchmark problems of different foams that have been tested in physical tests, and there are also example problems. So if we drill down into one of these examples, you'll find a model description and material property descriptions, and then some benchmark sort of force displacement data to help you zoom in on setting up the right type of elements in the analysis. So once I defined the foam bump stop, I used a basic linear elastic model for the Kevlar. And the rubber came from an example model of a pretty analogous system. It was actually from a rubber air spring in the Abaqus example library. So the material constants and other things were sort of there and validated against tests, so that's nice. One other option that we have, if we have a test data from rubber, is that we can define a material property based on that test data. It's taking them a second to load. And so with that, we can come into the test data and validate it against validate the fit of that against different material models built into Abaqus. In this case, we use linear uniaxial test data for and other types of tests. Basically, the test, and then you can run an analysis that fit is against the given material model that you select. So here I'm gonna look at the properties of this air spring. In the shell section, we can define that as a basic rubber, but then further under the options, we can define a rebar layer. So here in that layer, we define a cross-sectional area, distance from the center, and then an orientation angle. So for this orientation angle, we need to define what the main direction of the skew angle is. So for this case, I defined a cylindrical coordinate system at the center of the air spring. So then we can come into material orientation, and we'll pick some regions to apply this orientation to. And we're going to choose a coordinate system, the cylindrical coordinate system at the center. And we want to say that we're going to align the normal direction with axis 2. All of our normals are oriented outward, radially from the center, and the one axis is pointed longitudinally with it. So once we get our material properties assignment set, we'll come into step, and we have the step for pressurization, displacement, and bump defined. And after we define those steps, we can come into the load manager. And here's where we would say we'll fix the bottom at the initial during pressure that's propagated or it's held fixed. And then through the displacement, we're going to drive that 86 millimeters. And for the bump, we'll drive that 20 millimeters. Pressure and increased up to, and then it's turned inactive, which essentially locks the volume and pressure before displacement, and then the top is fixed all the way through the analysis. So once we've defined our material properties and our load conditions, I'm going to go ahead and just go into the results for this model. So here we have the 3D representation of that model. We can take a section cut again to kind of get a better picture of what's going on inside, and I'll just animate this through the time history. So you can see the initial pressurization sort of deform the air spring, and then it's driven up to where the elastomer is, the bump stop hits the top. If we want to look at some more detailed data about the air spring orientation, we can do that. There's basically, you track a variable relating the rebar angle. I need to turn off beam rendering to allow me to plot the actual. So here we can plot that rebar angle, which we defined as a 60-degree skew originally. So we can sort of track that through the activation of the air spring, and we can see how the change in that angle relates to the spring performance. So if we want to track some of the spring performance variables, I've got a couple different a few variables that we tracked here. So if we want to look at reaction force and displacement, we can plot that. So you can see the red line, which is displacement, is essentially held static while it's pressurized, and as this displacement is driven up the ramp, the force response increases linearly until you encounter the bump stop, and then you have a pretty steep increase in the resistance of the spring, which you'd expect, driving the spring to bump. You can also plot that with pressure. So there's quite a bit you can do to characterize the system with just a few design input variables. With that, I've gone through a couple analysis and some of the options you have available. So I'm going to back over to Glenn, and thanks for joining and following along.
Cool, thanks, Tim. All right, let's just reconnect the screens here. Hey, so just to recap those three applications. First one, we showed golf ball. The unique elements of that are some really complex material behavior within the ball, a very dynamic event, a very fast-acting event that we use a technique called an explicit solver for. Perfectly suited for that type of collision or impact action, and able to get a great result out of that. With the pipe element, that's a really common study that people in pipeline and structural analysis, where you're looking to embed that pipe in the soil and see how it reacts to some sort of soil movement, whether that's an earthquake or some other soil movement. And the unique thing about that one is that we're able to create really detailed models of the soil property along the length of the pipeline, from information like geological surveys and stuff like that. So really rich, deep information to dig into that. And lastly, with the air spring that Tim shared, we're just looking to characterize the performance of these devices so that we can try different design alternatives. And the unique thing that Abaqus offers here, on top of the material and being able to put in the Kevlar reinforcement, is the ability to step through load actions where it's initially pressurized, then we add a second load action where we push it into its rest position, and then we simulate almost a bump in the road. And we call that load stepping behavior, and that's one of the key benefits of Abaqus as well. This is a tiny subset of what Abaqus is able to achieve. And one of the neat things about it is that when you purchase Abaqus or lease it, it's available